Good morning, students. Today is the lecture number 4. The title of today's lecture is Convex Sets and their Properties. So, we will be talking about some definitions and some examples of various definitions like convex sets, convex hull, convex linear combination, extreme points, polyhedrons, hyperplanes, polytopes and generating hyperplanes, cones and edges. Apart from the definitions and examples, we will also cover some basic theorems and see how these concepts of these definitions that we are going to talk about are applicable to the theory of linear programming and how they are useful for this topic. At the end of this lecture, you will be given some questions to solve. So, first of all, let us define what do we mean by a convex set. Now, in general, all the definitions that I am going to discuss today are going to be related to any n dimensional space, where in general n is a positive integer greater than or equal to 2. So, we define a set S in an n dimensional space, that is R n, a real n dimensional space, is said to be convex if it satisfies the following property, that is, for all x and y belonging to the set S, we have lambda times x plus 1 minus lambda times y also belongs to the set S, where x and y are the points belonging to the set S, whereas lambda is a real number between 0 and 1. It can also take the n values, that is 0 as well as 1. Now, please note that the notations that have been used are capital X and capital Y. This indicates that they are n dimensional points which belong to the set S. So, in general we are talking about n dimensional space and n dimensional sets. If you look closely at this definition, we find that this definition tells us that a set S is said to be convex if the line segment joining any two points of the set also belongs to the set completely. So, for this let us look at some examples. Now, in this slide we see 6 examples where we can show that no matter any 2 points you take in the set and draw a straight line joining these 2 points, then the line segment joining these 2 points will completely lie in the set itself. Please note that this box, the rectangular box, also is a 3 dimensional box, and it indicates that if you take any 2 points and draw the line segment joining these 2 points, then that straight line is expected to lie into the set S, and that is the reason why these are all examples of convex sets. On the other hand, let us look at these examples. These are all examples of non-convex sets. Now, what does this mean? It means that even if you can find just one single combination of any 2 points such that the line segment joining these 2 points does not belong to the set, then that means that it is no longer a convex set. And this is what we see here in all these examples. I have drawn such a situation where the 2 points are taken and the line segment joining these 2 points is shown to lie not, it is not lying completely in the set S, and that is the reason why these are non-convex sets, examples of non-convex sets. Now you would say, why did I particularly choose these combination of points? The answer to this is that according to the definition of convex set, this should be satisfied for all such points x and y belonging to the set S. So, even if you get one just combination which violates this condition, then that means the set ceases to be a convex set. So, in order to check whether a given set S is convex or not, usually all the time it is not possible, you can show it graphically. Therefore, we need to apply the definition of the convex set. So, in this example, the set S1 is given to be x such that modulus of x is less than or equal to 1. So, in order to show that this is a convex set, what we will do is we will take any 2 points x1 and x2 belonging to the set S1, and since x1 belongs to S, therefore, it satisfies the condition modulus of x1 should be less than or equal to 1. Similarly, modulus of x2 should be less than or equal to 1, because both of them belong to the set S1, and we have to make sure that lambda should lie between 0 and 1 both inclusive. Therefore, we want to look at this condition lambda x1 plus 1 minus lambda x2. Now, why we are looking at this expression? We are looking at this expression because this expression indicates the set of all points lying between x1 and x2, because we are assuming that the value of lambda is between 0 and 1. So, let us now solve this inequality. We get lambda x1 plus 1 minus lambda x2, and the modulus can be taken inside, and the lambda is, because it is a real number, so lambda can be pulled out, and you get lambda times x1 plus 1 minus lambda times x2. Now, since modulus of x1 is less than equal to 1 and modulus of x2 is less than equal to 1, so therefore, this entire inequality will also be less than or equal to 1. So, that means what we have done is we have shown that this expression lambda x1 plus 1 minus lambda x2 belongs to the set S1, because we have shown that lambda x1 plus 1 minus lambda x2 modulus is less than or equal to 1, and according to the definition of the set S1, this point also belongs to the set S1. Therefore, S1 is convex. Now, let us take another example, and we see that this, we want to check the convexity of this set S2, where x2 is given by x such that modulus of x is equal to 1. So, that is the circumference of the unit circle, where x belongs to Rn. Now, everybody can visualize that this circle of unit radius, that is the circumference of this circle, is not a convex set. But how to prove it? It is not convex. Let us take 2 points x1 and x2 belonging to the set S2. That means that x1 belongs to x1, and of course, we have to make sure that both of them are distinct points, that is x1 should not be equal to x2. So, since they belong to the set S2, therefore, x1 and x2 both have modulus equal to 1. Now, if we will prove this theorem with the help of contradiction, and that is that let us suppose that lambda x1 plus 1 minus lambda x2 is less than or equal to lambda times x1 plus 1 minus lambda times x2, and of course, the value of 0 the value of lambda has to be between 0 and 1. The equality in this condition, that is equality will be possible if and only if either of the following conditions hold. So, what are those conditions? First one is that x1 is equal to 0, second one is x2 is equal to 0, and the third one is that lambda x1 is equal to mu times 1 minus lambda x2, where mu is greater than or equal to 0. Now, where does this condition come from? This condition comes from the fact that if it is a multiple, lambda x1 is a multiple of 1 minus lambda x2, only then will this condition be equal to 1. So, this in this inequality less than or equal to, we are trying to investigate under what conditions this inequality will become an equality. And we have seen that these are the three possibilities. Number 1, x1 is equal to 0, number 2, x2 is equal to 0, and number 3, lambda x1 is equal to some scalar times 1 minus lambda x2, where this scalar which I am representing with the help of the symbol mu is greater than 0. Now, let us investigate each of these conditions separately. So, what do we find? Since x1 and x2 there are the modulus is equal to 1, neither 1 and 2 hold. So, what was that condition? We were expecting that x1 should be equal to 0 and x2 should be equal to 0. So, since this condition holds that x1 mod and x2 mod is equal to 1, so it is not possible that both of them will be 0, either of them will be 0, none of them will be 0 in fact. Therefore, now we only remain to check is the third condition. Now, in the third condition, if the third condition is satisfied, then it is necessary that lambda x1 is equal to mu times 1 minus lambda x2. That means, you can pull out the lambda x1 is equal to mu times 1 minus lambda x2, and this modulus will remain inside and the scalars will go out. That means that the scalar lambda should be equal to mu times 1 minus lambda, and this means that x1 is equal to x2. But this is a contradiction, because this is not true, because we have assumed that x1 and x2 should not be equal amongst each other. Hence, 3 is also not true. Therefore, what do we conclude? That lambda x1 plus 1 minus lambda x2 absolute value is strictly less than lambda times absolute value of x1 plus 1 minus lambda times absolute value of x2, which is equal to 1, and so we conclude that lambda x1 plus 1 minus lambda x2 does not belong to the set S2, and this means that S2 is not a convex set. So, in general, the method for proving that a set X is convex, we need to show that if you take any 2 points in the set S, then the line joining those 2 points should also belong to S, and if we have to show that a given set S is not convex, then we have to, by some method of contradiction, show that the line segment joining these 2 points does not belong to the set S. Now, another definition is regarding the convex linear combination. The definition is as follows: let xi belong to Rn. So, what is this xi? Xi's are the points, let us say x1, x2, xn. So, suppose there are n number of points which belong to the set Rn, and let us suppose that we have some scalars lambdas be non-negative real numbers such that their summation, that is lambda of V is equal to 1. Then this point, this new point which we will call as x, which is given by lambda 1 x 1 plus lambda 2 x 2 plus lambda n x n, is called the convex linear combination of all the points where these points are given by x 1, x 2, x 3 up to x m. So, in other words, this combination where the scalars should have their sum equal to 1 is called the convex linear combination of the points x 1, x 2, x m. Now, let us come to a theorem. The theorem says that for a set S to be convex, it is necessary and sufficient that every convex linear combination of points in S also belongs to the set S. Now, please note that this is a necessary and a sufficient condition. So, both ways the logic should work. Some interesting set theoretical properties we would like to look at. So, the union of convex sets. Now, you can see that here is the yellow circle is representing the set S1. Similarly, the green circle is representing the second set, that is the set, let us say S2, and we want to look at the union of these two sets. So, the union of these two sets is given by this total area, and if you take any 2 points in this union and draw the line segment joining these 2 points, you find that this line segment is not completely lying in the union. Therefore, the union of convex sets need not be convex. Now, when can this be convex? So, I can leave this as an exercise for you. Under what conditions can the union of two convex set also be convex? So, this is very simple, just think about it. As I have mentioned, it is the union may or may not be convex. So, I am asking you, you have to think of a situation under which the union of two convex sets should also be convex. Next, let us look at the case of intersection. So, this is the set S1 and this is the set S2, both of these circles are convex, as we can very well see, and also the intersection of these two circles, that is this region over here, this is the intersection and you can very well see that it is convex. So, the intersection of any two convex sets is also convex, this is always true. Now, let us look at another theorem, theorem number 2. It says that the intersection of two convex sets is also a convex set. This is exactly the same example that we have just now done. We will like to prove it. So, how to prove it? Let us see. Let S1 and S2 be two convex sets and we will take any 2 points, let us say x1 and x2 belonging to the intersection, and we need to show that the convex linear combination of x1 and x2 should belong to the intersection. So, how do we do it? Let the convex linear combination, that is y, be equal to 1 minus lambda times x1 plus lambda times x2. This is the convex linear combination of x1 and x2, where lambda lies between 0 and 1, both inclusive. Now, since x1 and x2 belong to the set S1, therefore, we can say that x also belongs to S1 because it is the convex linear combination. Similarly, x1 and x2 belong to S2, this implies the convex linear combination also belongs to S2. So, therefore, what we have proved is, we have proved that X also belongs to S1 and X also belongs to S2, and according to the definition of intersection, X also belongs to S1 intersection S2. So, what we have proved is that given any 2 points x1 and x2 belonging to the intersection, we have shown that their convex linear combination, that is given by X, also belongs to the intersection. Hence, the theorem is proved. Please note that this theorem can be easily extended for any finite number of sets. So, if you have, let us say, S1, S2, S3, Sk, then the intersection of these finite sets, finite number of sets will also be convex. Now, suppose we have a convex a set which is not convex. Can we design a definition by which we can associate a convex set with that non-convex set? And the answer to this is yes. The definition of the convex hull tells us this. So, the convex hull of a set S is the intersection of all convex sets of which S is a subset. Please note that in this definition, it is not necessary that the set S is convex. In general, S may or may not be convex. So, the definition says that the convex hull of a set S is the intersection of all convex sets of which S is a subset. It is the smallest, in fact, it is the smallest convex set which contains S. Now, usually the notation for convex hull is written like this, that is within brackets S. If S is convex, then both of them are same, that is S is given by convex hull of S is the set S itself. However, if it is not a convex set, then they are different. Let us look at some examples. So, here is the set S on the left hand side. We have this L shaped figure, and you can see that this is not a convex set. S is not a convex set, because if you take 2 points over here and you join the 2 points, then the line segment joining these 2 points will not lie completely in the set S. So, according to the definition of convex hull, this is what the convex hull will look like. So, it is consisting of this entire region, and you can very well see that this convex hull is a convex set. Another example. So, here we have a figure on the left hand side, which again you can see is not convex. So, we want to see what will be the convex hull of this. So, if you draw a line joining these 2 points, then this region is going to look like this, and this is what is the convex hull of this set S. So, on the left hand side we have the non-convex set S, and on the right hand side we have the convex hull. So, this is the set S and this is the convex hull of that set S. So, some more theorems. Theorem number 3, the convex hull of a set S is the set of all convex linear combinations of points in the set S. Now, this theorem can be proved intuitively, because that is the way the convex hull is defined. So, I can leave this the proof of this theorem as an exercise. Next comes the theorem number 4. If S is closed and bounded, then the convex hull is also closed and bounded. So, again this is a very simple result and you can prove it yourself. Theorem number 5. Every point of the convex hull can be expressed as a convex linear combination of at most n plus 1 points of the set S contained in Rn. Now, this is a very interesting result and we want to look at it more closely. So, suppose we will take the example of R2 and let us suppose S is a subset of the 2-dimensional space and S is given by the set of all x satisfying this condition, that is x is equal to x1, x2, x3, x4, where each of these xi's are the vertices of a quadrilateral. Then the convex hull of S is either the convex quadrilateral or the convex triangle formed as shown below. Now, what does this mean? Let us look at it closely. Now, the figure on the left hand side shows that the 3 vertices S1, x1, x2, x3 are satisfying this property, whereas on the right hand side it is showing that it is a quadrilateral. So, therefore, with the help of this example we can conclude that any point in the convex hull can be expressed as a convex linear combination of at most 3 points of this set S. Next comes the definition of vertices, or in other words extreme points of convex sets. So, first of all let us look at the definition of a point x of a convex set S is an extreme point or a vertex of S if it is not possible to find 2 points x1 and x2 in the set S such that x is equal to 1 minus lambda x1 plus lambda times x2, where the value of lambda lies strictly between 0 and 1. So, that means a vertex is a boundary point, but not all boundary points are vertices. For example, let us take the case of a circle. So, any point on the circumference of a circle is a boundary point, but it is not a vertex. Also, a point of S which is not a vertex of S is an internal point of S. Let us look at another theorem, theorem number 6. All internal points of a convex set S themselves constitute of a convex set. Now, the proof of this is, let us suppose V be the set of all vertices of the set S, then the difference, that is S minus V, is the set of all internal points. Therefore, let us take any 2 points x1 and x2 belonging to the set S minus V. So, if x1 and x2 are belonging to the set S minus V, we will show that their convex linear combination also belongs to the set S minus V. Therefore, x1 and x2 belong to S, hence x can be written like this: x is equal to 1 minus lambda times x1 plus lambda times x2. This also belongs to the set S, where lambda lies strictly between 0 and 1, which by definition is not a vertex of S. Hence, x belongs to S minus V, which means S minus V is a convex set, and hence the theorem is proved. Another concept related to convex sets is the definition of a convex polyhedron. It is defined as follows: the set of all convex combinations of a finite number of points x1, x2, xm is the convex polyhedron spanned by these points. So, that is the definition of a convex polyhedron. Theorem number 7, the convex polyhedron is a convex set. This is very clear because that is the way the definition has been given. Theorem number 8, the set of vertices of a convex polyhedron is a subset of its spanning points. Now, let us look at this example in order to understand this theorem. There can be spanning points which are not vertices. Now, how does this example help us to understand this? Let us look at these 4 points A, B, C and D. Consider the points A, B, C, D in the 2-dimensional space such that D is in the inside of the triangle formed by the vertices A, B and C. So, as you can see, the point D is in the interior of the triangle formed by A, B and C. Then what do we find? We find that the 4 points which span the triangle ABC, but D is not a vertex, and that is what the theorem tells us. Now, let us look at another definition. This definition is about a hyperplane. It is defined as follows: let x belonging to Rn and let C be a constant rho vector that is not equal to 0. So, C is a non-zero constant rho n vector and alpha is a real number. Then we define a hyperplane by the set of all x such that C transpose x is equal to alpha. Then we also defined closed half spaces as the set of all x such that C transpose x is less than or equal to alpha, or the other side, that is set of all x such that C transpose x is greater than or equal to alpha. Similarly, we define the open half spaces as x such that C transpose x is strictly less than alpha and x such that C transpose x is strictly less than alpha. As you can very well see that a given hyperplane divides the entire space into 2 half spaces, that is one on one side of the hyperplane and the other on the other side of the hyperplane. So, they can be closed half spaces if you take the inequality into account, and if it is a strict inequality then it can be defined as the open half spaces. In order to visualize this concept, let us look at this hyperplane. You can see that this hyperplane divides the space into 2 parts, one above the hyperplane and one below the hyperplane. And as I mentioned that if less than equal to is considered, then it is considered to be 2 half spaces, and if it is only a strict inequality then they are said to be open half spaces. Okay, some more definitions. Polytope and generating hyperplanes. This is defined as follows, that is the intersection of a finite number of closed half spaces is called a polytope. That is, if you have more than one hyperplanes and you take their intersection, then the half spaces they intersect and that intersection is called a polytope. The hyperplanes producing the half spaces are called the generating hyperplanes of the polytope. Let us look at an example. Now, in this example you find that this is a polytope because it is obtained by the intersection of a finite number of hyperplanes which are dividing the space into lower and upper categories. Similarly, we can define higher dimensional cases of polytopes as is shown here in this diagram. Theorem number 9. A point x of a polytope is a vertex if and only if this point xv is the only member of the intersection set of all generating hyperplanes containing it. So, this is intuitive, that is the way the vertex is defined. Corollary: the set of vertices of a polytope is finite. So, as an exercise you can try to prove this statement. Since the set of generating hyperplanes of a polytope is finite, the family of subsets of this set is also finite. Therefore, we can say that a vertex by the above theorem is nothing but the intersection of the subsets of generating hyperplanes. Hence, the number of vertices is necessarily finite. Some more definitions: the cone and edge. So, let us define the cone first. The polytope generated by hyperplanes, all of which intersect in one and only one point, is a cone. And similarly, a line is in a polytope is said to be an edge of the polytope if the line is the only intersection of these generating hyperplanes which contains the line. Let us take some examples to understand this. The polytope C1x less than or equal to alpha 1, C2x less than or equal to alpha 2, x belonging to R3 has the line of intersection of the two planes as its edge, that is polytope C1x less than equal to alpha 1, C2x less than equal to alpha 2, C3x less than or equal to alpha 3 where x belongs to R3, such that the three planes intersect in one and only one point in a cone with the point of intersection as the vertex. It is an unbounded polytope with three edges which are the intersection of the planes taken two at a time, and the edges are half lines with the vertex as an end point of the edges. Now, let us look at what do we mean by the vertices of a closed bounded convex set. Theorem 10 tells us that if a set S is non-empty, closed, convex and a bounded set from below, or let us say above, then it has at least one vertex. Similarly, theorem 11 tells us if a set S is non-empty, closed, bounded and convex, then number 1, S has at least one vertex, and number 2, every point of S is a convex linear combination of its vertices. Theorem 12 tells us that the optimum solution of a LPP, if it exists, then it will either lie on a vertex or on a edge of the feasible region. Now, this theorem 12 tells us what is the importance of studying these concepts of convex sets and polytopes with respect to the linear programming what we are studying. in order to understand this theorem, let us look at the graphical method that we did in the previous lecture, and we saw the example of the unique solution case. Now, this example illustrates that we have an LP as shown here, that is maximization of 3x1 plus 5x2 subject to x1 plus x2 less than or equal to 2, 5x1 plus 2x2 less than or equal to 10, 3x1 plus 8x2 less than or equal to 12, and both x1 and x2 are greater than or equal to 0. Now, we find that the feasible region is given in this figure, which is shaded in green color to indicate that this is the feasible region. The solution of this problem is shown here at this vertex, and you can see that the solution will either lie on one of the vertices or it will lie on an edge, and by edge we mean the line segment joining any two vertices. In fact, any point inside the feasible domain will have a higher value objective function value than a lower objective function value than the maximization, because it is a maximization problem. So, therefore, any point lying inside the feasible region will have a lower value, that is an inferior value as compared to the maximum. Therefore, maximum will occur only at the vertices or on a edge. Similarly, let us look at the example of multiple solution case. Here again we find that the problem is maximization of 2.5 x1 plus x2 subject to 2.5 x1 plus 5 x2 less than equal to 15, 5 x1 plus 2 x2 less than or equal to 10, and x1 and x2 greater than or equal to 0. We find that the maximum lies on all points lying on the line segment joining these 2 points, that is 1 comma 2.5 and 2 comma 0. That is the solution lies on the edge. In fact, it lies on all points which are obtained on joining these the line segment joining these 2 points. The line segment joining 1 comma 2.5 and 2 comma 0 is actually this line 5x1 plus 2x2 is equal to 10, and if you try to find out the coordinates of this, then any point which lies between these 2 points will be of the type given by t comma 10 minus 5t upon 2, and its objective function will also be 5, and hence this will give the optimum solution. And as I explained in the last lecture, that there will be multiple such points, and in fact there will be unbounded number of such points. Theorem 13. The feasible domain of a LPP, if it exists, is always a convex set. Now, again this is one of the reasons why we were studying convex sets with respect to linear programming problems. On the other hand, if you take a look at a feasible domain of a non-linear programming problem, then you find that the feasible domain of any non-linear programming problem may or may not be convex. So, here is an example to show you that the feasible domain of a non-linear programming problem could be convex. As you can see that this feasible domain is nothing but a torus of 2 circles, and that is x1 squared plus x2 squared is less than or equal to 4, and similarly x1 squared plus x2 squared is greater than or equal to 1. Some more examples of convex sets with respect to linear programming. As I said, the line segment joining any 2 points is always a convex set. So, here is an example to show you that if you have this line segment A and B, so this line segment is a convex set. Why is it convex? because if you take any point C on this line segment, then it can be written like this: C is equal to lambda times A plus 1 minus lambda times B, where the value of lambda lies between 0 and 1. In fact, if this strict inequality is converted into inequality, that is, if equality is also included, then it will also take into account the endpoints A and B. So, but in this example I am trying to show that the line segment joining any 2 points A and B is also a convex set. And also let us look at unbounded sets. A unbounded set may or may not be convex, and an unbounded feasible domain of a LPP is convex. Unbounded feasible domain of a NLPP is not convex, that is, for example, the exterior of a circle. So, in the end I would like to conclude that we have studied today some concepts related to convex sets and their properties, and we have also seen how they have a lot of importance with respect to our subject of concern, that is linear programming. We have also seen a number of theorems which shows some of the results related to the convex sets and their properties. In the end, I would like to mention that you should check out these examples and exercises. I want you to check the convexity of the following sets. Number 1, S given by x and y, where x and y satisfy the conditions 3x squared plus 2y squared is less than or equal to 6. As you can see that this is a nothing but a circle. The set S given by x y such that 6x plus 2y is equal to 5. As you can see that this is nothing but a straight line. And the third example is the set of points x1, x2, x3 given by these conditions x1 plus 2x2 less than or equal to 5, x1 minus x2 plus x3 greater than or equal to 6, x1 greater than or equal to 2, x2 greater than or equal to 0 and x3 greater than or equal to 0. The fourth example is the set S given by the points x1 and x2 such that x2 is greater than or equal to minus the absolute value of x1. And the fifth example is the set S given by x1 x2 such that x1 squared plus x2 squared is less than or equal to 4 along with the point in the 2-dimensional space given by 10 10. So, with these 5 examples I conclude this chapter. Thank you.